So let us talk about classifications of singularities. Before that, I'd like to introduce what are zeros of a complex function. Let's say you have a function f of z. Z0 is said to be 0 of f if f of z0 gives you 0. For example, you can take this guy f of z equal to z minus 1 into z plus I. So it is clear that the zeros of this function, zeros of f of z, these are 1 and negative I. So these are the zeros of f of z. It means when you plug in z equal to 1 here, then you get 0. And you plug in z equal to negative I, then you'll get 0. So that is why it is called 0. 0 of f. So, but this is one example. When it comes to the second, let me take f of z equal to, let me take z square. So z square minus 1 plus 2iz. So this is the function. So can you tell me what are the zeros of this function f of z? So you can see that f of I, not okay, if I take f of I, let me see what happens. This is I square minus 1 plus 2 times of I square, I into I. Okay, so this gives me I square minus 1 plus 2I square. So this is what I have, 3I square minus 1. It's not equal to 0 anyway. So f z equal to I is not a 0 of this function. So next let me see whether z equal to negative I, is it a 0 of this function or not. So if I substitute negative I, this is negative I square minus 1, this is plus 2I, and this is negative I, and I get exactly I square minus 1 minus 2I square. So this is what you have, negative 1 minus I square. Okay, but you know what is I square? I square is negative 1. So negative 1 minus of negative 1, this will give you negative 1 plus 1 will give you 0. Therefore, z equal to I, this is a 0 of f of z. But here, if you observe that this is nothing but z plus I, sorry, here I should write z equal to negative I. So z plus I whole square is nothing but this expansion, z square minus 1 plus 2iz. Okay. Now if you look at the multiplicity of z equal to negative I, which is 2. Why? Because 2 times it is a root. It's not just a single root. It is a quadratic equation, and 2 roots of this equation are nothing but negative I only. Okay. So now, how to know the multiplicity? So how to know whether 0 is of what order? Let's say here I'll say that 0 is of second order 0. Okay, or we can call it as a algebraic multiplicity. So let me define what is a 0 of kth order. That's what we call, in other words, you can call algebraic multiplicity. You can simply say multiplicity. Z0 is said to be a 0 of kth order. Let me say 0 of f of kth order if f of z0 is 0. First of all, it should be 0 of f, and next the first derivative at z0 must be 0, even the second derivative must be 0, and even if you go till k minus 1th derivative, all must become 0. Okay, and the kth derivative at z0 must be non-zero. So we say z0 is a 0 of f of kth order, or simply it is a root of f with algebraic multiplicity k if all derivatives till the k minus 1/3 order are 0, but the kth order derivative is non-zero. Then I can say it is a root with multiplicity k. Okay, so for example, if I take f of z equal to z plus 1 whole cube into z plus I into z minus 2i. Okay, so now the zeros are zeros of f. These are -1, -i, and 2i. So these are the zeros. So when it comes to the multiplicity of -1, that is 3. Why? Because it is a root for 3 times, and you can check with this definition. It's up to second derivative. When you substitute -1, you will get 0, and the third derivative will be non-zero. And how about the multiplicity of -i? That is 1. Okay, so when the multiplicity is 1, we call that is a simple root or a single root. You can use any word. So the multiplicity of 2i, that is also 1. Therefore 2i is a simple root. Okay, now let us come to the singularities. So now the singularity, we are going to classify them into 2 types. One is isolated, another one is non-isolated singularities. So let's talk about singularities. So we define, okay, let me start with an example. That's better. Suppose if I take this function f of z equal to principal logarithmic function log z, and here this side I'll take this function f of z equal to 1 by z plus 1. Okay, or let me take some more. So 1 by z plus 1 into z plus 2 into z plus 10. Okay, now can you tell me what are the singularities of this function? See, remember I am taking principal logarithmic function here. So this is actually principal logarithmic function. So what are the singularities of this principal logarithmic function? Do you remember? Do you remember this branch cut for a principal logarithmic function? And we proved that this principal logarithmic function is not continuous along this line, that is the negative x-axis, but everywhere else we do not have any issue. And of course we proved principal argument function is not continuous and limit does not exist on this line. Okay, so now this function, it's going to be analytic everywhere except on the negative x-axis. Okay, so therefore the singular points of or singularities of f of z, these are, you can start with any z0 where z0 belongs to, z0 is a point in the negative x-axis. So z0 can be any point on the negative x-axis. So on the entire negative x-axis, this function is not analytic. So now let me write every point on a negative x-axis. You can call x-axis or the real axis. Let me call x-axis, negative x-axis. is a singular point. So that's a singular point of log z. Okay, so we got infinitely many, of course, uncountably many singularities for this function. Okay, but whereas the other side, if you look at the singularities, so the singularities are -1, -2, and -10. Okay, here there is a small similarity. The singularity is on the negative real axis, but here every point on the negative real axis is a singularity. So let me say how they were located. It's like, let's say this is the negative x-axis. So here I can have -1 and then -2 and then -10. So this is how they were given. These 3 points are only the singularities of the given function. Okay. Now we are going to classify them into 2 parts. So one which comes under this case and another one this case. Let me tell you what is that case here. See here, if you give me any 2 singularities of this function, okay, I can create a neighborhood around these 2 singularities so that no intersection point is coming inside it, isn't it? So even between, suppose if you give me -2 and -1, I can create a neighborhood around these 2 so that no common point is coming inside it. Or in other words, can you draw a neighborhood around a singular point so that that is the only singular point in that neighborhood? It means, can you isolate the singularity here? I hope in the second case you can do it. Why? Because you can create a circle around -10, in which only -10 is the singularity. That's it. Similarly, you can create a neighborhood around -2, in which only -2 is the singularity. Similarly for -1. It means you are able to isolate the singularity here. But let us come here. Let us come to this case, principal logarithmic function. Can you isolate the singularity here? See, every point on the negative x-axis is a singularity. Okay, so let me pick up one point. For time being, let me take -2. So is it possible to create a neighborhood around -2 so that -2 is only the singularity inside that neighborhood?
No, sir.
It's not possible. Why? Because many points are coming inside that neighborhood, right? Because every point on this line is a singular point. Therefore, here we cannot isolate the singularity. Whereas here we can isolate the singularities. So we are going to classify singularities into 2 types. One case is isolated singularities. Isolated singular points, and here non-isolated. So again, these isolated singularities we are going to classify into 3 types. So one, that is removable singularity, another one pole, and another one essential singularity. Okay, let me draw the picture again. So the singularity here and non-isolated, isolated. So let me define what is an isolated singular point. Z0 is said to be isolated singular point of F if there exists a neighborhood that is n delta of Z0 which does not contain, if there exists a neighborhood n delta of Z0 such that f of z is analytic on this deleted neighborhood n star of Z0. It means in that neighborhood Z0 is only the singular point. So no other point is a singular point in that neighborhood. So that's what I mean. Okay, simply you can write it in words. We say Z0 is an isolated singularity if there exists a neighborhood around Z0 which does not contain any other singular point. Okay, so now let us see what are the classifications of isolated singularities. So now this we are going to classify isolated singularity based on the Lorentz series expansion. So Lorentz series expansion will help us to classify these singularities. So do you remember when the Lorentz series exists? Let's say when you have some Z0, okay, and when you have some annular region like this, either you can take an annular region like this, or simply this is also called an annular region when Z0 is a singularity. Okay, so in this annular region, when you know F is analytic, so we have a series expansion, right? So in that series expansion, we mainly have two terms. So one term is this, that is f of z equal to summation an into z minus z naught whole power n. We already discussed this part is called analytic part. Okay, plus we'll have the another term, that is summation bn into 1 by z minus z naught whole power n. Okay, and this part has a name, we will call it as a principal part. So based on the principal part, we are going to define, or we are going to classify this isolated singularity. Okay, so the moment you have an isolated singularity, we can write a Lorentz series expansion for that, and in which you look at the principal part and you classify the singularity. Okay, so we say the function has removable singularity at z0 when the principal part is 0. So when it has removable singularity when the principal part is equal to 0, it means there is no term which involves 1 by z minus z0. When there is no principal part, we say it has a removable singularity. Okay, so the next thing, we call it as a pole of order m. Pole of order m if the principal part, the highest term in the principal part is 1 by z minus z naught whole power m. Okay, so here in this case, so the principal part will have finite number of terms, finitely many terms, and the maximum order is m. So then in that case, we call it as a pole of order m. Okay, and the next thing, what is left now, one thing is when there is no principal part, that is what we call removable singularity. And the next thing, suppose if you find it up to degree m, if you find the principal part up to degree m, then we say it's a pole of order m. Whereas the other possibility is infinitely many terms. So if there are infinitely many terms in the principal part, so in this case we call the singularity is nothing but essential singularity. Okay, so based on the principal part in the Lorentz series expansion, we are going to classify these singularities, isolated singularities. Okay, so let me give you some examples. For example, you take sine z by z. So now my function is f of z equal to sine z by z. So what is the singular point here?
Zero, sir.
Yes, singular point of f that equal to z0, which is 0. Here in this case it is 0. Okay, so let me see, is it an isolated singularity? Is it an isolated
Yes, sir.
singularity?
Yes, sir.
Yes. Why? Because this is the only singularity. Definitely it is an isolated singularity, no question in it. So here, let me see the Lorentz series expansion. What is the Lorentz series expansion? Expansion about Z0, where Z0 is nothing but 0. So we know how to express sine Z by Z. So this is nothing but 1 by Z into the expansion of sine Z is Z minus Z cube by 3 factorial plus Z power 5 by 5 factorial minus and so on. Now multiply with 1 by Z, and the region of validity we need to write 0 less than mod Z less than infinite. And when you multiply, you get 1 minus Z square by 3 factorial plus Z power 4 by 5 factorial plus and so on. So do you find any principal part in this expansion? Is there a principal part? It means is there some terms which involves 1 by Z, 1 by Z square, something like that?
No, sir.
No. So there are no terms which looks like 1 by Z, 1 by Z square and all. So therefore there is no principal part here. There is no principal part. Therefore, what kind of singularity is this?
Removable singularities.
Exactly. So there is no principal part in the above series expansion. Therefore, Z not equal to 0 is a removable singularity of sine Z by Z. So therefore Z equal to 0 is a removable singularity of sine Z by Z. Okay. Now let us talk about another function. So the second problem, f of Z equal to sine Z by Z square. What is it? So first you see what are the singular points. There is only one singular point, and the singular point of f, that is Z not equal to 0. So this is anyway isolated singularity. So let's see what type of singularity is it. Let's classify. So first you need to write Lorentz series expansion about 0. So sine Z by Z square, that is 1 by Z square into Z minus Z cube by 3 factorial plus 5 by 5 factorial minus and so on. So now I can see 1 by Z minus Z by 3 factorial plus Z power 3 by 5 factorial minus and so on. Okay, now where is the principal part? Do you
1 by
find
Z.
any principal part in this expansion?
1 by Z, sir.
Yes. So there is one term. So this is what analytic part. Z cube and all. This is what analytic part. Whereas this is what exactly the principal part. Okay, so how many, what is the highest power of 1 by Z here in the principal part? Only 1, isn't it? This is the only term and its power is 1. Therefore, now the singularity is going to be a pole of order 1. Therefore, Z not equal to 0 is a pole of order 1. For f of Z equal to sine Z by Z square. So remember one thing, whenever you have a pole of order 1, we call that it is a simple pole. Like when you have 0 of order 1, we call it as a simple 0. Similarly here, we call it as a simple pole. Simple pole, it means you should understand that it is a pole of order 1. Okay. Now with the help of previous two examples, can you tell me what type of singularity does it have? Sin z by z power 10. Be careful. So now I know z equal to 0 is a singular point. Now what type of singularity is this? Is it a removable singularity or pole of order something, or is it an essential singularity?
Pole of
Pole
order.
of order 9, sir.
Pole of order 9. Okay. So this is a pole of order 9. Why? Because if you look at the expansion of sin z by z power 10, so you'll exactly get 1 by z power 10 into all these terms, z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. And you could observe that here it has terms like z power 9 minus 1 by z power 7 into 3 factorial plus 1 by z power 5 into 5 factorial minus 1 by z power 3 into 7 factorial plus and so on. So now it has the principal part and as well as the analytic part somewhere here. Okay, in the principal part there are 9 terms if you observe, and the highest power of 1 by z is 9. Okay, therefore it is a pole of order 9. Okay, now let us look at other functions. Next example, f of z equal to 1 by z plus 1 into z minus 2. So write the singular points here and try to classify them. But you can ask one thing, sir, is it necessary to write Lorentz series expansion every time to decide what kind of singularity is it? It's not needed. See here, first you see what are the singularities. Singularities are z equal to -1 and 2. These are the two singularities. Whenever you have a finite number of singularities, they are always isolated. Why? Because any finite number of points can be separated. Okay, if you give me two distinct points, I can always separate them in a complex plane. Okay, so these are isolated singularities. Now I need to classify them. So to classify them, it is enough to see 0 of the denominator, like z equal to -1 is a 0 of the denominator of order 1 or with multiplicity 1. Okay, so then it is going to be a pole of order 1. It is a simple pole. So z equal to -1, this is a simple pole, and similarly z equal to 2, this is also a simple pole. Okay, if you get a doubt, let's do one thing. Let's try to verify. F of z equal to 1 by z plus 1 into z minus 2. Okay, I'd like to decide whether z equal to minus 1, what kind of singularity is it? So what should I do? I have to expand this series in terms of z plus 1. So 1 by z plus 1 readily available, and the next what I have is 1 by z minus 2. So this I have to expand it. So 1 by z plus 1, this into, it can be written as, let me write it as z plus 1 negative 3. And this equal to 1 by z plus 1. You can take 1 by 3, negative 1 by 3 common. So from that you have 1 minus z plus 1 by 3. So negative 1 by 3 you keep it out. 1 by z plus 1 you have it here. So summation n equal to 0 to infinite z plus 1 by 3 whole power n. Okay. So now when you write the expansion, negative 1 by 3 into z plus 1, this multiplied with 1 plus z plus 1 by 3 plus z plus 1 by 3 whole square plus and so on. And you can see when you multiply with 1 by z plus 1, so you'll have only one term, that is 1 by z plus 1, and the rest is analytic part. Okay, therefore it is a pole of order 1. It is a simple pole. Z equal to 1 is a simple pole. Similarly, you can see that z equal to minus 2 is also a simple pole. And one more thing we can observe. By using limit also we can find whether it is a simple pole or pole of order m, okay, or a removable singularity. So let me tell you how. So first let me take a removable singularity. Let's assume that f of z has removable singularity. It means what? Let me assume this. It means the Lorentz series expansion of Lorentz series expansion of f of z, which is equal to, you'll only have analytic part. The principal part will be 0, right? That is summation n equal to 0 to infinite a n into z minus z naught whole power n plus 0. The principal part will be 0. Now if you see limit z goes to 0 or z goes to z naught, f of z, I want to see this. Okay, now I will apply the limit to the summation. Limit z goes to z naught, summation a n into z minus z naught whole power n. Okay, you know this summation is convergent, therefore we can take this limit inside. So when you do that, simply you'll get summation a n into zeros. So this is nothing but 0. Oh, do you get 0? Sorry. You'll have a constant term, right? Why? Because this summation will start from n equal to 0 to infinite. So the limit is going to be a naught plus a1 into 0 plus a2 into 0 plus and so on. So finally you end up with a naught. Okay, so if a function has removable singularity, then limit at that point exists, and that will be equal to the constant term here. So if you know the f has singularity, if you want to classify, you can simply look at its limit. Okay, see, for example, let us look at limit of sin z by z itself. Limit z goes to 0, sin z by z. And what do you know? This is nothing but limit, sin z by z is limit is 1, or you can apply L'Hospital rule as well. Cos z by 1, cos 0, that is 1. Since this limit exists, it is equal to 1. Therefore, z equal to 0 is a removable singularity. Okay, so let me write a note. If f of z has removable singularity at z equal to z naught, that implies limit z goes to 0, f of z exists. Sorry, z goes to z naught, it's not that 0. Z goes to z naught, f of z exists. Now let us talk about a simple pole. Suppose if I have a simple pole, it means what? A simple pole at z naught. Okay, so then f of z has this Lorentz series expansion, that is 1 by, let me write it, b1 by z minus z naught plus the rest is nothing but this an into z minus z naught whole power n, where n equal to 0 to infinite. Okay, this is what the Lorentz series expansion if f of z has a simple pole at z naught. Now let us do one thing. You can see that limit z goes to z naught, f of z. Definitely can say that this does not exist. This does not exist. And if you look at the other limit, that is limit z goes to z naught, if I multiply with z minus z naught, that is f of z into z minus z naught, which is nothing but, what is z minus z naught into f of z? b1 plus, now from here on you'll get z minus z naught whole power n plus 1, isn't it? That is limit z goes to z naught, you'll have b1 plus summation n equal to 0 to infinite an into z minus z naught whole power n plus 1. And you could see that what is its limit. So this is nothing but b1 plus 0. This is b1. Therefore we can see that if f of z has a simple pole at z naught, then limit z goes to z naught, z minus z naught into f of z exists. That's what. Then limit z goes to z naught, f of z, which doesn't exist, and limit z goes to z naught, z minus z naught into f of z exists. So this is what happens if you have a simple pole. Similarly, if you have a pole of order m, then what can you say? If you have a pole of order m at z naught, so limit z goes to z naught, z minus z naught whole power m into f of z, this limit exists, and limit z goes to z naught, z minus z naught whole power k, f of z does not exist. Where k is strictly less than m. Till m minus 1 limit, it doesn't exist, but the moment you take z minus z naught whole power m, the limit exists. Then you can say that it has a pole of order m. Okay, but when you take an essential singularity, whatever m you take, the limit doesn't exist. So that is what for essential singularity. It means if you cannot find any m for which the limit doesn't exist, we can say that singularity is an essential singularity. Okay, now let me give you an example. Let me continue the number 4. Okay, Now this time let me give you 5. F of z equal to e power z minus 1 by z. E power z minus 1 by z. So find the singularities of this function and classify it. First of all, tell me what are the singular points? What are the singular points of f? Hello?
Zeros.
What is it?
Zeros.
Yeah, correct. Z equal to 0 is a singular point. Now, let me see what kind of singularity is it. So, to see that, let me see what is limit z goes to 0 f of z. Why? Because the singular point is 0, no? Or let me write z naught here. So, that equal to limit z goes to 0 e power z minus 1 by z. And you see, when you plug in 0, you are getting 0 by 0 form. Okay, so when you get 0 by 0 form, you can take help of L'Hospital rule. So when you take it, limit z goes to 0, the derivative of e power z minus 1 is e power z minus 0 by the derivative of z is 1 using L'Hospital. So now this is equal to, now what is the limit? E power 0, which is equal to 1. Therefore it exists. Therefore the limit exists. So you can say that z equal to 0 is a what kind of singularity?
Removable.
Exactly. So therefore the conclusion is z equal to 0, z not equal to 0 is a removable singularity f of z. Okay. And next problem. F of z equal to 1 by z cube into z minus 1 into z plus 5 whole square. Write all the singularities and classify them. It's an easy job. Can you tell me what are the singular points here?
0, 1, minus 5, sir.
Exactly. 0, 1 and negative 5. So these are the singular points. So can you classify them? Z equal to 0, that is a what? And similarly z equal to 1 is a, and z equal to negative 5. So how about z equal to 0? Is it removable singularity or pole or essential singularity? You can use the limit definition. When you multiply with z cube and when you take the limit at 0, that exists. But when you multiply with z square and take the limit, it doesn't exist. Okay. So therefore, it is going to be a pole of order 3. Z equal to 0 is a pole of order 3. See, when you have a rational function like this, directly you can take the power. That's it. Okay. So now z equal to 1 is a pole of order 1. Or in other words, it is a simple pole. Okay. Next, z equal to negative 5. This you tell me. Hello?
2, sir. Order 2.
Yeah, pole of order 2. That's it. Okay. So I'll give you one more function. F of z equal to e power 1 by z. Now tell me what is the singular point here and what kind of singularity is it? So definitely limit z goes to 0 e power 1 by z, that doesn't exist. Even when you multiply with z power k, it doesn't exist. So in that case, you do one thing. So first of all, let us identify what are the singular points. So z equal to 0 is a singular point of f. Now I look at the Lorentz series expansion of e power 1 by z. So Lorentz series expansion, that is e power 1 by z, which is equal to summation 1 by n equal to 0 to infinite. So I'll have 1 by z whole power n by n factorial, isn't it? Or you may write it like this: n equal to 0 to infinite 1 by n factorial into z power n. This is what the expansion, right? So let me write in terms of like the summation. So the first term, when you plug in 0, that is 1, plus next term 1 by z, next term 1 by 2 into z square, next 1 by 3 factorial into z cube, plus 1 by 4 factorial into z power 4, plus and so on. So how many terms are there in the principal part? This entire thing is a principal part itself. So how many terms are there in the principal part?
Infinite, sir.
Infinite, sir.
Exactly. There are infinitely many terms. Therefore, what kind of singularity is this? So z equal to 0 is it removable or pole or essential?
Essentials.
Yes. This is an essential singularity. Okay. So these are the classifications of a singular point. Based on the Lorentz series expansion, we classified. We can simply look at the summary here. Yeah. So singularity which is divided into non-isolated, isolated. Yeah, we didn't discuss about any non-isolated singular points. Yeah, we discussed just one example, L and Z. We have some other examples as well. I'll tell you in the next class. So isolated, we divided into 3 categories based on the Lorentz series expansion. One is removable singularity, another one is pole of order m, another one is essential singularity. So these are the classifications of singular point of a function. Okay, so this is all for today. I'll stop it here. Let me know if you have any questions or doubts.
No, sir.
Okay, so we'll meet in the next class then. Bye.